Let's do it. Where we go from here, where we go from last module, is we are freeing ourselves from the tyranny of circuits. Break free, man! We're going to do physics in outer space or in air, far away from any batteries and resistors and stuff like that. So we're going to be free. We're going to be analyzing it, which isn't to say that there's not ever going to be stuff. We will talk about metals and conductors and insulators. There will be one more electronic circuit component. Don't forget everything you learned about current. That stuff is still important. But the big thing that we want to talk about that we're going to generalize, we're going to get deeper into is voltage. I want you guys to have a more sophisticated, more nuanced understanding. I introduced voltage in the context of batteries give it, resistors dissipate it, transform to and from electrical potential energy form. We're going to go deeper. We're going to take it deeper. And along the way, in fact, this very day, I'm going to introduce a new term called electric field. And electric field is huge as well. Electric field is not actually that hard once it clicks. But warning. It does take a second to click. You do actually have to think about it. You cannot just rely on equations. That reminds me. I am not going to preach to the choir here, but I am going to warn everybody, every single person, that there are a few guiding principles and a few equations that stitch together into a web of like 25 equations. If you rely on memorization and just looking for what letters can I plug in for what numbers can I plug in for what letters, you're screwed. There are 6 different equations for voltage. You can't just memorize without thinking about meanings. Or you seriously cannot even get you'll be getting G's on the tests. There is a big reason why I'm always giving analogies. There's a big reason I'm giving practical, concrete, real world examples for this stuff. I feel like some of the big things that 50% of the class missed in the midterm 1, there were questions that over half of the class missed. Were things where people were looking for numbers to plug in and not thinking about the principles that go into it. Okay, not thinking about what does this mean? Does this make sense in this context? Again, there are 6 voltage equations, and if you end up guessing which one to use, you cannot possibly hope to be passing. Watch out. Watch out. You have been warned. You have to be paying attention when we're talking about getting an intuitive sense of this, a gut feeling, a nature of what's going on. What does it mean? Not just, can I plug numbers in for letters? Okay, so today, I actually want to start with the hard stuff and end with fluffy stuff. I did it the reverse order for the the 3 o'clock section. We can start with electric charge because it's been a little bit since we've talked about charge, and particularly what is a coulomb. These are 2 of your homework questions and a quiz question if I recall correctly. And then the big boy, the big guy, is electric field. We're going to be using him not every day for the next month, but frequently. The connection between electric field and everything else is also super important. Then we got a fluffy behavior of static electricity that is aimed, it is designed to give you, again, that better gut feeling for what is this stuff and how does it act. It's not numbers, it's ideas to get some kind of intuition, to get some kind of gut feeling, to get some kind of how does this stuff actually behave and work. In short, this is the stuff that if you ignore it, you're going to totally miss half your test because you don't know what's going on. You're just looking for keywords and failing thinking about stuff. So watch out. Also, this is like well over half of this homework set. This is going to be, we're going to cover most of this week today, and we're going to fill in the gaps. Is that what it says? Fill in the gaps on Wednesday and do more practical applications. But I want to front load this. The fluffy stuff is easy peasy, I think, is in my experience, most students have heard of most of this. Conductors, what's an insulator? What's a conductor? You've heard of this stuff. Even if you can't necessarily define it. Huh? Hey, you get an A. Good. Like puns. Anyway, hey, that's enough telling you what I'm going to tell you. Let me tell you. Charge. I introduced this on day one, but day one was over a month ago, right? So I don't expect that you instantly remember it. What's a coulomb? You guys remember what a coulomb is? 1 coulomb worth of charge is nothing but a dozen eggs. Well, a mole of atoms. Well, it's a certain multiple, a certain very large number that we measure electrons in, protons in, because the individual ones are really super duper small. Mitzi, I'm not screen sharing? Here I am. Oh, I haven't written anything yet, Mitzi. Question is, here, what's a coulomb? You should be sorry, Mitzi. What's a coulomb? Again, I answer my question by saying a coulomb is nothing but a dozen. What's a dozen? Give me a dozen. Someone hold up a dozen. A dozen what? A dozen fingers? Give me a dozen dollars? I don't know. The idea of the dozen is we don't like selling individual eggs, so we sell them by the standardized package of 1 dozen at a time. And everybody knows a dozen means 12 of that thing. What the hell is a mole? Atoms, molecules in a lab are inconveniently small. We don't like to measure them out 1 atom at a time. So we invented this number called the Avogadro number, 6 times 10 to the 23rd, because a practical sample. You know, my finger has something like Avogadro's number of atoms in it. Something like that. Something like that. 18 grams. Yeah, something like that. So that's the idea of the coulomb. 1 coulomb is the electrical oomph of 6¼ times 10 to the 18 individual oh my God, individual charge. Maybe I should say individual charge particle. I can't spell. You know what? Figuring out what word individual is left as an exercise. Individual charge particles. By individual elementary charge particles, I mean protons, electrons, quarks. No, that's not true. But you don't need one. Yeah, so I do want to make one point. If I say a coulomb worth of electrons, 6 times 10 to the 23rd electrons, and I were plugged into an equation, usually I plug in negative 6 times 10 to the 18, 6.25 10 to the 18. Q in an equation can plug in negative for electrons, positive for protons. But I'm frequently just going to abuse terminology and assume that everyone knows that electrons are negative particles. And if I've got a numerical solution where I'm asking what's the voltage here, voltage will end up relating to the individual charge. If I've got voltage near an electron, I will talk about, I've got 1 nanocoulomb worth of electrons. You need to know that means Q is negative 1 nano. Everyone know that electrons are negative? Hopefully this isn't a sophisticated concept. If I want to be very precise, I should say 1 coulomb is 6.25 10 to the 18 protons, or absolute value of electron charge. Google Form A. Tell me if you can. Oh, let's build this up. 1 egg is a 12th of a dozen, right? Right? How many eggs in a dozen? Google Form A. How many eggs are there in a dozen? If 1 egg is a 12th of a dozen. Really hard question here. Really hard question. One more time. If each egg is a 1/12 of a dozen, then how many eggs is 1 dozen? Oh, good. Everyone's getting this right. All right. That's correct. Swell. Don't say it. 12. Huh? Please.
Yeah, so when you say that -6.25 into 10 to the power 18, this is like 1 coulomb of electron.
Sure.
But it, like we consider the sign thing in the vectors. So, but like we are.
I will always in this class emphasize the intuitive sense of pushing and pulling this way or that way. We're not going to be doing positive negative vectors.
Okay, no, my question is something else. Question is that why are we putting the negative sign in front of a magnitude of charge? Like the number of charge.
Well, that's the thing. If I use equations that have charge in them, like QBD, Q for an electron is a negative event. So, and that flips the direction of B cross B. If I just said Q is, 1 coulomb worth of electrons and ignored the fact that electrons are pushed the opposite direction as protons, I would get the wrong answer. I would not be predicting the results accurately. That's not really important. So I can't simply say there are 6 billion electrons and plug in 6 billion for charge. So I'm talking about the electrical effect of an electron. I will use it. If I'm talking about how many, I will always use a positive. That's actually a really important point. Let me emphasize here a second thing about the coulomb before I give you the answer for how many eggs are in a dozen. If I ask you, and I do on this homework, by the way, if I ask you how many electrons are blank coulombs, how do you count how many? Is the answer to how many fingers do you have held up? Is that ever a negative number? No. If I ask you how many electrons are blank coulombs worth of electrons, you will always tell me a positive number because counting things that are sitting there is always a positive number. If I ask you the electrical charge measured in coulombs of 5 electrons, then you would give me a negative number. The electric charge versus a counting how many. Conceptually, they're about as closely related as you can get. Does it make sense, the distinction that I'm making? The electric charge is the electrical effect of these things. A how many question is, can you count them? Great. Now, going back to the form, going back to the previous thing. Most people now correctly identified that if there are 1/12 of a dozen is 1 egg, then there are 12 eggs in 1 dozen. What's the relationship between 1/12 and 12? I claim that one way that I can interpret this is to say that 1 egg is equivalent to 1/12 of a dozen. I claim that I can convert this, not just by memorizing the word dozen means 12, but I can convert this by multiplying both sides of this equation by 12. Are not 2 eggs the same thing as 2/12 of a dozen? Are not 5 eggs 5/12 of a dozen? Are not 12 eggs 12/12 of a dozen? When I have 1 coulomb being 6 times 10 to the 18 individual protons worth of charge, can you tell me, Google question B, what is the charge on 1 proton? Can you find the electrical charge measured in coulombs, I should say, And by the way, the thing about the dozens was I'm telling you how to do this. Look for connection. Also, please watch order of operations when you plug into your calculator. You will need this for the homework, by the way. And I think one of the quiz problems. Oh, I haven't looked at that recently. Almost here. Remember, 1 coulomb makes a very large number of individual particles, right? 1 coulomb is 6 billion, 600 million particles. Does it make sense that if 1 coulomb is a butt ton of particles, that 1 particle is a butt ton of coulombs? Does it make sense if 1 coulomb is a lot of individual particles, that 1 particle is a lot of coulombs? Is that logically sensible? Check your answer and turn to your neighbor and check their answer. So I do have some nonsense coming in. Okay, la respuesta correcta. The correct answer is I can take the equation that 1c is 6.25 10 to the 18 p's and divide both sides by the same number. I can always take any equation and divide both sides by the same number. If I take 1 divided by 6 by the I get 1.6 times 10 to the negative 19. These things are equivalent facts. I would like to encourage you not to memorize them as separate things. That wastes brain space. If you know how many electrons, protons, whatever, in a coulomb, I would like you to be able to, if I tell you there are 5 electrons, convert that to coulombs without just memorizing steps and nonsense. Okay. Also, sanity check yourself, please. I had a fair number of people tell me that there were billions of coulombs in 1 electron or 1 proton. If you have 1 egg, is that 144 dozen? No. Okay. Not too many, but too many. Okay, so that's charge. And that's all you need to know about charge. Now let's talk about the biggie, the big boy, the electric field. And I want to introduce this by connecting it to stuff. Make a new page. Big space on your page. Here's a great fraction of the study guide for next midterm. Potential. And I spell, I can't. Potential. Yeah. FUEV. FUEV. What you say to the Tesla driver in front of you that's being a real jerk? FUEV. There are relationships between these quantities. If you know the relationships between these quantities. 24 equations become 6 equations at the end of the module. You won't need to know 24 different things. You only need to know a few different things. If you don't understand, make sense of, internalize the meaning, then you're gonna have a 1 in 6 chance, 1 in 4 chance of getting the right answer, of using the right formula in any given context. So, with that hopefully motivating you to think about this, let me ask you, what is the relationship between U and V? Potential energy versus voltage. What is 1 volt in terms of joules? 1 joule per coulomb. 1 volt is 1 joule per coulomb. Or if I had joules, what could I do? If I have potential energy is U joules, I could say that the voltage is energy divided by charge. Bam! That's its meaning. This is the always true equation. Never has any exceptions whatsoever, ever. Voltage is intimately most connected, best defined in terms of the energy carried by some charge. Although I'm going to make that statement a little bit more sophisticated later. Not today. There is a completely different relationship between force that charges feel and electric field. Just kidding, I lied. It's exactly the same relationship. Electric field asks, how much force does something feel per coulomb charge? What is the ratio of force to charge? Or you could say, if I know how much force is exerted on blank 3 coulombs of charge, then the force wouldn't twice as many particles, wouldn't 6 coulombs of charge feel twice as much force? If I know the force on 3 coulombs of charge, doesn't it make sense that if I've got twice as many things feeling that push, wouldn't I have twice the force? So the ratio of force to charge is a constant. Google Form C, solve for force. Google Form C, tell me what is the force equation. How much force does an individual charge feel from an electric field? We're going to come back up to this. Leave some space in your notes. Check your algebra. Check yourself before you wreck yourself. Okay, the correct answer is if I want to express the force on a charge in terms of the charge and the electric field, I do not say mass times acceleration. F equals ma is a true statement, but that's not what we're talking about. I simply solve this equation for force by multiplying both sides by Q. Force is charge times field. Okay, so I already wrote something algebraically equivalent. Why am I writing it this way? I think that if you stare at this equation and think about the following, you really get a deeper understanding of what the hell field means. Every force has 2 things, a feeler and a dealer, yeah? And if you want to understand how something reacts and moves, you need to understand all the forces. You want to understand how a feeler actually accelerates, you need to understand what all the dealers are doing, right? Right? Okay. Electricity, we do the same damn thing as with before. If I want to find forces on a feeler, I need to think about what the dealers are doing. Dealers feelers, that's it. I am partitioning the universe into the object that I am studying, bam, and everything else is electrical push and pull on that thing. Feelers, dealers. I will talk about the charge, the force on a test charge. And a test charge is the feeler. Let me write that down. The thing which feels the force. Oh, who wasn't in my class last year? All right, so a feeler and a dealer, or who wasn't in my class and has never heard those words, feeler and dealer. Okay, so remember in 111 in introductory physics, physics 1, we talk about object A pushes object B. By Newton's third, then B also pushes back on A. But whatever we say is experiencing a force, that force is caused by something, right? Every force is caused by some object. I call the thing which causes the force the dealer, and the thing that feels the force, you'll never believe this, the feeler. Okay? So the test charge, all you need to know about the test charge to find out how hard other charges push on it, all you need to know is how much charge it has. One second. E is the electric field due to dealers, which I will call source charges. Okay, so I will use these words a billion times. Source charge, test charges. Sorry, test charge, source charges. Notice there could be multiple charges that are causing an effect, but I'm only ever going to talk about one charge at a time feeling effects. Just like in 111, we said focus on the forces on some object. Lots of things push on that object, but you just look at that one object at a time. That's the test charge. Everything pushing or pulling on the test charge electrically are the source charges. There is a convention. I don't remember if your homework system uses this. I apologize if it does not. It's a really good convention. I promise to use it uniformly in here. Lowercase q is used only when I am talking about something which feels electric field, or that has an energy. The test charge is always lowercase. Other charges pushing or pulling on that test charge are always capital Q. Capital Q causes, little q feels. Capital Q's are the causes. Little q is the thing that feels those pushes, the feeling. Yes, it is. It is very similar. QB, QE.
So above those two formulas, if we,
You can absolutely push them.
yeah, we can just equate that.
No. Magnetic force and electric force are two different kinds of forces. Total force would be add them. QE plus QVB is the total force on the charge. Yes, so last chapter we found that force magnetic equals QV cross B. This chapter we're finding the electric field is QE. Magnetism and electricity are related but not the same subject. The total force, if I've got both things going on at once, is QE plus QV cross B. They're not necessarily equal unless you know the total force is zero. No, not in general. I mean, I can think of a scenario in which it is, but that is not always true at all, ever, even a little bit. Just like, it is not true that friction is always equal to weight. They're both a force. That doesn't mean that they're always equal. Did y'all hear that, by the way? Just because I've got a formula for force doesn't mean that that formula for force is describing the same thing as another formula for force. You can't always say that QE is MA. MA applies when you got a total force. If the only thing you're feeling is electrical forces, then you could say Q equals MA. Sure, but not always. Okay. How do I calculate the amount of charge on a test charge? Oh, well, don't calculate it. It's either given or everything else is given, you solve for it. This is simple. This is stupidly simple. The only thing you need to know about a test charge to find out how hard it's pushed or pulled, how much energy it has stuff, is how much there is of it. Electrically, how much charge, how many free protons or electrons. But for electric field, there's actually several different parts to that. Easy, hard. I shouldn't point at the Q, I should be pointing at the E. Electric field is more sophisticated. There will be, I think, less than half a dozen, something like half a dozen formulas for electric field. I want you to know that force per charge is the only thing that is universally true. Let me give you one that is true in a particular circumstance so you can see. Whoopsie. Here is a electric field formula. Capital Q, whoopsie. I'm going to make the meaning of R a little more complicated later. But for now, I want to describe it as from source charge to test charge. I want to emphasize this equation is sometimes true. V is sometimes R I times R. V is always energy divided by charge. Remember that? V is not IR in a battery. V is battery voltage equals IR when you got an R. This is true for a point charge model. What's a point charge? I should spell that out. Harsh, question first. Good. Question.
Yeah.
That's always true. That always equals QE.
Yeah, so when you said that the small q, the test charge,
Mhm.
and single charge.
That's all you need to know about the test.
Yeah, so that single charge on which all the other charges are,
Pushing, precisely.
yeah. So if it is a single charge, then shouldn't it be always 6.5?
Ah, very good. Thank you. Excellent. Little q and big Q are not necessarily talking about just one electron or one proton at a time. If it is, you would plug in 1.6 10 to the negative 19, sure. But this is true anytime. Actually, this leads exactly into where I was going with this. This is anytime the charges, the electrons, the protons, whatever, are bunched up together enough that you don't care about where they are. They're all together in one place, geometrically a point, or close enough to a point that you don't care about how far apart they are. Let me say that again, because that's exactly actually where I was going with it. When I say point charge, I am saying all the electrons or all the excess protons are located so close together that I don't care about the fact they're not actually here. Saying the exact same point. I'm gonna black hole. So I'm gonna say if you put, charge the tip of a pin needle to 1 nanocoulomb, 1 nanocoulomb is still 6 billion electrons. They won't all be exactly at the same point, but they'll be close enough to each other that I don't care the fact that the tip of the needle out there is some space, let's say. The distance between them is small compared to the distance to where I care about. Okay, muy importante. F equals QE, always. So E equals F over Q, always. E is KQ over R squared when I've got point charge creating it. I'm going to end this section by saying every, write this down, charged particle emits, exudes, creates. There's a fourth synonym that I like. Causes. That's not the word I was looking for, but it fits. Exerts. Whatever, I'm out of space. Electric field. Electric, I can't spell. So how does A affect B? A creates a field, B fields the field and is pushed thing. That's how two charges interact. Sure. That's all you need to know for now. We're going to go much in detail later. And we're in particular going to make R more interesting. Sure.
And then another part of the next loop also has a barrier and this pushes each other against.
No. I don't care what the test charge makes. I don't care about the fact that the test charge also makes an electric field. If the test charge has a charge, Q times whatever the other guy makes, that's all I need to know to find the force. Hey, that's really important too. For question, think about this. Every charge makes a field. Fields push on each other. No! I don't want you to think about it like that. Test charges make their own fields. Yes, don't think about them. The test charge doesn't need to make a field to feel other guys' fields. Do you guys remember from last semester, I hammered on this a bunch. Hopefully the people that didn't take me had heard this from their instructors, that the Earth makes gravitational field around it, which attracts objects nearby. Yeah? Do you also, I mean, hopefully, yeah. Do you also remember that you yourself make a gravitational field? It's just stupidly weak. Yeah, you gravitate too, not just your mama so fat. Everybody, every piece of matter in the universe gravitates everything. But you don't have to think about the fact that you make your own field to calculate m times g. Your mass, Earth's g, make up your weight formula, your gravitational force formula. Your charge times Earth's electric gravitational field make up the weight formula, make up the force formula. There is an intimate relationship, analogy, I should say, between mg and QE. Mass, m is how much of something there is, Q is how much of there is electrically, G is how much a gravitational, a planet pulls on you, E is how much a nearby other charge pulls on you. And you don't have to think about the fact that you yourself gravitate or you yourself have an electric field around you to calculate your charge times its field.
I remember at the starting of the lecture, you said that, like electrons or the charges don't make field. Field is like the source of the field.
Wait, they don't make field what? Hold on.
So the charges, starting with the lecture, you said charges don't make, like what the source from the field down is,
The test
they charge, they possess field, but they are not make field.
the test charges absolutely make their own field, but we don't need to calculate them, think about them. We shouldn't think about the field of the test charge.
Then
Every charge makes a field, but the thing that you care about, the thing that you're calculating the forces on, the thing that you want to find the force on, ignore its field.
so the make field of the possess.
Yes, both are great words. Does the Earth possess a gravitational field around it, or does it make the gravitational field? Sure. I think either are good descriptions. Well, we could say you want to go down and be rigorous. Every charge we have ever measured, if you put a charge near it, experiences a force. We call the ratio of the force experienced by that test to the amount of charge on that test, we call that the field. Caused by, made by, emitted by. Great. That's your first take on field. Electric field, force per charge, and the electric field for a point charge. There will be more. But now we're done with all the hard parts, and we have a chance to go into some light and fluffy stuff. You guys want a 5-minute break? 2-minute break? Yeah, take two. The next part, there are facts to know, important facts, but you can relax a little. 2 minutes by the clock. Blah, blah, blah.
So at the starting of the lecture, I still did not, that doubt did not get cleared. So
So you didn't get what?
the doubt which I just asked about like the
Yeah,
production.
I don't remember saying.
You said that we don't know where the field comes from. So it's like it's there. You said it's there. Like let's say magnetic field. So in the magnet, the field is always there, but we don't know where it comes from. It's like a standard thing. You said something like that.
That's a true statement. I didn't remember that I told you that.
You did like
Okay, so yes, at a deep foundational level, no one's ever observed a field.
okay.
At a deep theoretical, philosophical standpoint, field could be an imaginary mathematical construct that we use to explain the results of experiments, but so is everything in physics.
Yeah, that is exactly.
Does it exist? Well, I can measure the force it exerts on nearby charges, but does it exist?
Mhm. That is where I was actually confused when she said that, charges make their own field. I was like, how
Like our.
both, statements work together.
Near every charge, other charges will be pushed and pulled
Yeah, so
in a
that,
predictable fashion.
so, that, so the results we get with those physics, the rules of physics, that is, so that is why we use field to explain those relations and all that. Okay, got it.
Good.
Yeah.
Well said, too. Good. Okay, it's time. No. I mean, the thing is, I think we'll still get out of here early. It's not it's a fair number of facts, but there's no conceptual detail. I don't need to go into 1,000 examples and analogies and mental models for this stuff because it's stuff, I think a lot of it is stuff you already heard. So I think we'll still get out of here early. Have some hope, my friend. Yeah. Okay. I hear you. I want dinner too. What moves? An atom is, well, electron is about a millionth, varies, depends on the atom, but a millionth-ish the size of the rest of the atom. A millionth as much mass as the rest of the atom. And if we consider one electron, take one electron and the rest of the atom apart, well, if I take one electron off of the rest of the atom, how much charge has this atom got? If I take an uncharged, neutral, ordinary atom, and I take one electron off, I've got one electron worth of charge here. How much is left here? How much charge have I got on the atom? I would say positive 1 unit of charge. There's one proton that's not canceled out. Yeah? Right? Okay. So the one proton that is no longer feeling its friend, its partner, is left to cause effects and feel effects, feel fields. And the bare electron that you've taken off feels the fields. The big formula that we just came up with, or I just gave you rather, QE, the charge, Q, is the same. And the electric field that you apply from other charges around it might be the same. If I put these charges in outer space and let them race each other, so the electron feels the same force as the rest of the atom that is now ionized. F equals ma. If force is the same and mass is 1,000,000 times bigger, A is bitsy. The rest of the atom barely recoils. The electron speeds out of it. My point is, electrons small, easy to move. If you kick a child versus kicking a football linebacker, the child is much easier to kick, right? Wait, oh God, that's terrible. Don't do that. What moves? We're going to talk about a fair number of electrical effects here and there and everywhere. And what moves just like in a circuit, what shuffles around is the electrons. Is that due to the fact that protons can't move, rest of atoms can't move? No. As far as I know, though, it's just the fact that they're so much huger, same force, very different mass, very different results. So, what moves? Electrons. When electrons move, they leave behind proton. So suppose I've got a conducting metal rod. If it's metal, of course. I've got a metal rod somewhere. There's a metal cylinder. Piece of wire, whatever. And I attract an electron to this side. Where'd that electron come from? Some atom somewhere in the material, right? Yeah. Okay, so what have I got? I've got a plus left behind. As I'll show in a second. If I've attracted the minus from one end by an external charge, that will push the plus to the opposite end. Did this plus get pushed there? No. The minus was ripped off of it, leaving the plus behind. I will talk about charge goes to the right. If I've got a positive charge and I physically move it around in outer space, that's possible. But if we are, excuse me, If I do a static electricity experiment where I rub some balloon on my hair and touch those positive charges to somewhere, well, no, what's actually gonna happen is that the balloon doesn't place protons on another balloon. The balloon is going to attract some electrons off of that balloon. But what's the net effect? There are going to be fewer electrons on the second thing that you touch. There are going to be some of these pluses are now canceled out, and some of these pluses are no longer canceled out. The total amount of plusness is still the same as if you could smear protons around. So, what moves? Electrons. But from a practical standpoint, most of the time, I could still talk about positive charge goes there in a very sane way, even though what's actually happening is negative charge is leaving there. But you don't need to think about that unless it's explicitly told. Plus goes this way, minus goes this way. Okay. So far, so good? Electrons small, they move? Easy? Yeah, great. Conductor versus insulator. Hippies versus squares, man. Free love, conductor. I don't share my partner. Insulator. Monogamy, polyamory. What makes a conductor other than leading the train? What makes a conductor is that it is promiscuous with its electrons. The outer shell electrons are free to move from atom to atom. As one moves through a sample, other ones will probably come from behind, attracted to the pluses and left behind. But nevertheless, you don't have atom A and electron A bound together forever. Sometimes atom A will have electron A somewhere else, and it'll have gathered electron B, leaving behind nucleus B back here, which picks up electron C. I don't know, I don't care. My point is, they're swingers, they're hippies, they're free love, they're promiscuous, they're polyamorous. Insulators are what you learn about most of the time in chemistry class. They're monogamous. They don't share. They're not swingers. Their electrons are their electrons. Now, that doesn't mean you can't pull them. We'll talk on Wednesday more about this. But you can actually pull, twist, and partially separate electrons of an insulator away from each other. But what I'm going to talk about for the rest of this lecture is to really understand the motion of electricity is something where you can really move, where the electrons are rippable, offable. It doesn't take, that makes it sound like it takes force, where electrons are easily pushable around the material, and that's a conductor. What's a conductor? What kinds of things are conductors? What conducts electricity? Metals. Yeah. What doesn't conduct electricity? Lots of other things. Give me an example. Rubber. Ceramics. Glass. Hair. Air, too. Yeah, hair is not a good conductor. Your outsides, your skin is usually a pretty darn good insulator. You can touch a 9-volt battery. You may have done this in lab. You may have touched the terminals of a 9-volt battery and you didn't die, right? However, I do wish to point out, we're actually going to talk a fair bit about this in module 3, electrical safety lesson. If you cut someone apart with a razor blade and put, oh God, that's disgusting, never mind. Your warm, squishy insides conduct electricity very nicely. So you could kill a person with a 9-volt battery if they had open wounds that conducted the electricity. Yep. As long as the electricity is touching the warm, squishy blood and guts on the inside, That's a good conductor. The water.
Oh,
The water, well, to be precise, actually, pure water is an insulator. Did you guys know that? If you got deionized water in the lab, that's an insulator. But water is, you may have heard this rumor, very good at dissolving stuff. So you got water running through your pipes in your home, that's gonna be dissolving the metal ions in the walls of the thing. It's very good at being a good solvent. That's why we're alive. So it's actually the dissolved ion, the dissolved solutes in there that conduct electricity, but since that happens really well, good solvent, lots of ability to conduct. Good question. Okay, so conductor versus insulator, hippie versus square, polyamory versus monogamy. Holds on to the, freely flowing electrons versus holds on to individual electrons tightly. Come on, come on, come on. Now, a free object with some charges on him. This, most people get wrong. I got wrong 25 years ago when I first learned this stuff. Suppose I have 5 electrons. I put 5 electrons on a metal ball. Where do they go? Where do you think they go? Make a prediction. Draw it on your paper. Draw a metal ball and draw 5 little minus signs to predict where you think you'll end up finding them. Go on, do it, do it, do it. Draw a little circle, put 5 little minus signs around the ball where you think they would end up. I will remind you that like charges repel, duh. So they want to get as far away from each other as they can. Draw a metal ball, a circle, draw 5 little minus signs, predicting where you think. If I put 5 charges that can separate out on a little ball, where do they go? Where do you think they end up? Look, here's the wrong answer. I mean, I can charge up my hair, 5 electrons or whatever, touch them to a metal ball at this point. If it's an insulator, they'll just stay there. But in a metal ball, they can flow freely, right? I mean, that's what I just said. Where do you think they'll end up? Where do you think they'll end up, Jane?
like as equidistant as possible.
Well, that's the question. Is this as equidistant as possible? Who put this? Who drew this? Yeah? Okay, that's what I drew 25 years ago when I first learned this. It's wrong. As it happens, as far away as possible from each other. I can't prove this without count, I don't think. As far away as possible from each other means smoothly around the outside area. Smoothly around the outside area. Hey, let's draw a triangle. Suppose I've got a pyramid, like the aliens built. Yeah, there we go. There's a pyramid. Claim that if I charge a metal pyramid, the charges on it are going to distribute uniformly over the surface, not on the inside, all over the surface, but uniformly across the surface area. Equal number of electrons per square meter. Something like that, yeah? These are the surfaces now. I'm not drawing inside a triangular cross-section of something. I'm drawing on the surface of the pyramid. You can tell it's a pyramid because there's it's a perspective drawing. Look, Sphinx. See? Yeah, this is a perspective drawing. This is a cross-section. Okay, now, riddle me this, Batman. Think about that. Are charges spread uniformly through space, or are charges bunching up in certain places? Draw a little outline around an area like there. How many minuses have I caught? 1.5? draw an equal sized circle around one of the points. 3 minuses. And I didn't draw the fact that there'd probably be one at the tip top. 4. When you have pointy shapes, electrons will end up smoothly over surface area, means more densely over pointy regions. What's the point, unintended, of a lightning rod? You guys know? It's not just to catch the lightning. Not just. If lightning strikes a lightning rod, sure, conducting electricity preferentially down to ground through a safe wire is better. You know? Yes, to disperse the electricity. The point of a lightning rod is to allow ions to spray off, to ionize the air nearby, to break down the insulator quantity. If you've got a super sharp tip, those can spray off. The charges of the opposite sign to the cloud can spray off at the tip where they get super dense, at the needle tip. The point of a lightning rod, the other point of the lightning rod is to discharge the clouds before the lightning strikes. And the way they do it, the way we get strong enough field density at the place is to make a needle tip at that point. You pack as much surface area into the same place, the same volume. So you need to know for this free object with charge, free charges spread out uniformly over surface area. Not inside, not uniformly through the volume, as far as possible away, ends up being that they're free to stay wherever they want. Okay. So what happens if we're not free? And let me tell you, we are not free. Polarization. I'm going to take a big honkin' plus. Stay positive, everyone. That's a stupid barbell. Yeah, that's a better barbell. And I take a big honkin' plus and I bring it near a metal barbell. What happened? I don't know if you've heard this rumor, but opposites attract. And like charges repel. What's going to happen to the electrons inside the metal rod in the barbell? The electrons go which way? They're attracted, yeah? Which way is that? You're going to end up leaving the negative charges smeared out. They're not going to be right on top of each other, but they'll be smeared out towards, you know what? I don't want to draw it like that because that makes it look like there's some inside. They're going to be smeared out preferentially towards the left side. Those electrons will get as close as they can, hubba hubba, with their positive attractive partners. Where do the pluses, those protons left behind, end up? What do you think? Effectively, we can ignore the effect. We can ignore the fact that pluses aren't really moving. We can think about where would the deficits come from. Well, those plus charges are pushed as far away as possible from the applied plus. This is called polarization. I bring in an external charge and pluses and minuses in objects separate. Let me ask you this. What happened if I take this away? Come on, what would happen? These guys will attract to each other again and neutralize, right? I haven't added electricity. I haven't added either minus or plus to this barbell. I just pushed them apart. They still want to come back together, but this guy is pushing them apart. It's like, no, never mind. Let me ask you this then. And this is the last thing that I'm going to say today, except for that I love you. What happens if I take some scissors and cut the barbell's bar? What would happen? Would I suddenly be left with positive charges here and negative charges here? No, that's magnets. Magnets never have an isolated north and an isolated south. If I just make an incision in the metal there, narrow cut, nothing would change with the electricity, right? So I take an object, I polarize it, I break the object. What happens if I take the plus away now? What happened? Jane, what do you think happens? They redistribute along the bit that they're on. Can they get back together with their long lost loves? No, because the object is broken, the object is separated. You'll do this in lab. If I'm not greatly mistaken, oh God, did I take that out this year? You may or may not do this in lab this year. You will polarize an object, you will break it apart effectively, take two objects and pull them back apart, is breaking it apart. And you will see that after the polarized object has the polarizing thing removed, there will still be pluses and minuses. It's just they can't recombine, so they'll be spread out uniformly over the surface of their what's it. I want to emphasize, if there are 5 positive units of charge on this side, how many negatives were pushed over here? 5, right? The total amount of charge, it was a neutral object to start with. I never brought in an external charge and touched it in. I never introduced excess electricity. I just separated them, caused to separate and broke them apart. This is called charging by induction. And it's one of the answers to the homework question and where we're going to pick up things. Questions before we go? I didn't hear anything. You can come up here. I love you all. Goodbye early. Oh, sorry. 3 minutes early.
Container B for that question of the test that was like connected to a battery. How does the voltage change? I was like,
Did you get it?
yeah.
Hey! Yes, exactly. Yay!
Question.
Joe.